Welcome to Calculus. Today we will investigate finding limits using L'Hopital's rule, looking at the two indeterminate forms. We'll look at three examples. Our first example is the limit as x approaches 5 of the fraction square root of x minus 1 minus 2 over x minus 5. And we want to apply L'Hopital's rule. So we really need to remember what L'Hopital's rule says. Essentially, if I've got a limit of a ratio of two functions, so limit as x approaches some value c of f of x over g of x. And if I were to do direct substitution and found that this limit had the indeterminate form of either 0 divided by 0 or infinity divided by infinity, at that point I would, in normal circumstances, look for some strategy to get rid of that form. And what L'Hopital's rule allows us to do is to deal with that form using differentiation. And the way that L'Hopital's rule goes is if I can create another ratio, which would be the derivative of f over the derivative of g. In fact, we'll put this in a formal way. If the limit as x approaches c of the quotient there of the derivatives, and that equals some value L, then the limit as x approaches c of the original f over g will also equal L. So let's see how we can apply this. First of all, we have to determine whether or not I'm going to get an indeterminate form when I do direct substitution. So that's my first step. So here I'm going to plug in 5 for x, and I see I got square root 5 minus 1 minus 2. So overall, that's going to be square root of 4, which is 2 minus 2. That numerator is going to be 0. And that's all over. If I plug in x with 5, 5 minus 5 is also 0. So we do have an indeterminate form. That's one of the conditions to be able to use L'Hopital's rule. So at that point, I'm going to take the derivative of the numerator and the derivative of the denominator separately. So I'm not applying the quotient rule, I'm just thinking of these as two separate functions. So what I would say at this point is, all right, so we're going to apply L'Hopital's rule, and I always record that I've done that by writing L'Hopital's rule over that equal sign where I'm actually applying it. So I would say this equals the limit as x approaches 5. And I want to take the derivative of this numerator, so I can think that that square root of x minus 1 is really x minus 1 to the power of 1/2. So as I take derivative, that's going to be the power half as a coefficient times x minus 1. We'll treat this as a composed function there using the chain rule. And then I'll do half minus 1, which would be negative 1/2 for the new power. And then I multiply by the derivative of this x minus 1, which doesn't change much, that's just 1. And then the derivative of minus 2 would be plus 0. So I took the derivative of the numerator, and we'll simplify that. But first, let's take derivative of denominator. So derivative of x minus 5 is just going to be 1 plus 0. And now I do want to simplify. So at that point, I'm going to write equals. I don't have to write L'Hopital's because I'm not applying it a second time. So we're looking at the limit as x approaches 5. And I've got quite a bit that's going to fall out of this numerator. The 0 and the times 1 are going to fade away. But the half, I can let the 2 drop to the denominator. And since this fraction, or I'm sorry, this base to a power is a negative power of half, I could write that with the positive half exponent by letting it fall to the denominator as well. And that would leave just 1 in the numerator. And at that point, we can try direct substitution again. So I see that my x value is 5, so I'm going to plug it in 1 over 2 times parentheses 5 minus 1 to the power of half. And recall that power of half is the square root, so that's really 1 over 2 times the square root of 5 minus 1. Square root of 4 is 2, and that solves readily as 1 over 4, and we are complete. So in that instance, we applied L'Hopital's rule once in order to come up with a form that wouldn't give that indeterminate form 0 over 0. Our second example is this one. We want to take the limit as x approaches 1 of the function 3 times x minus 1 over natural log of x. So again, to use L'Hopital's rule, I have to establish first that if I do direct substitution, this limit's going to yield an indeterminate form. So we'll try that first. So I'm going to plug in 3 times 1 for x minus 1. So I see that numerator is going to be 3 times 1 minus 1 is 0. 3 times 0 is 0. And then for denominator, I have natural log of 1. So remember, when we say natural log of 1, we're really saying e to what power would give me 1. And that really can only be the power of 0. So again, I do have an indeterminate form 0 over 0. Since that it really is the criteria for using L'Hopital's rule, we're free to do so. I do want to rewrite this numerator just to make it easy to take derivative by distributing. So first, I'll just say that this is equal to limit as x approaches 1 of 3x minus 3 over natural log of x. And at that point, I'm going to apply L'Hopital's rule. So I'll write L'Hopital over the equal sign right as I'm applying it, L'Hopital's rule. And that equals the limit as x approaches 1. And recall how we do that again. I take derivative of the numerator. So derivative of 3x minus 3 is going to be 3 plus 0 over the derivative of natural log of x is the rational 1 over x. And at that point, I can simplify this fraction by multiplying by x below. That'll cancel my variable in the denominator. So all I've got in denominator is 1. We're going to close shop down there. And then times x above the 0 is going to fade away. So this simplifies at last to the limit as x approaches 1 of 3x, which is then going to just accept direct substitution. So we plug in 1 for x, and that gives us the limit equals 3. Let's take a look at a third example here. So here we're looking at the limit as x approaches infinity of e to the power of 2x over 2x squared. So if I were to attempt direct substitution with infinity, I would be plugging in infinity into the exponent, and I can just imagine that as I raise some base to an infinite power, the whole thing is going to approach infinity. So this would be infinity in the numerator. And then similarly in the denominator, if I plugged in infinity as a base raised to the power of 2, if I'm squaring infinity, that's a version of infinity. And what we see is the second main indeterminate form, infinity divided by infinity. So again, this limit is eligible for L'Hopital's rule. And we can immediately apply it. So we're just going to immediately write L'Hopital's rule over our equal sign. And we'll observe that that is equivalent to the limit as x approaches infinity. And take the derivative again separately of the numerator and the denominator. So the derivative of e to the power of 2x is going to be e to the power of 2x. Then I need to take the derivative using chain rule of the 2x. So that's going to be times 2. And then I want to take derivative of the denominator separately. Derivative of 2x squared is going to be 2 times power of 2 is 4x to the power of 1. And so I can clean that up by canceling the 2 and the 4 there. So this is now the limit as x approaches infinity of e to the power of 2x. So we're back to the original. That's not unusual for taking derivative of e to some power. And then down below we would have canceled a factor of 2 out of the 4, so it's over 2x. So again, I could attempt to plug in with direct substitution, but this infinity, again, if it goes into the power, is going to be e to a power of infinity, which is a version of infinity. And still, if I plugged in infinity to my denominator, 2 times infinity, I still have an indeterminate form. And that, again, highlights the usefulness of L'Hopital's rule. You can apply it multiple times. So if I'm still getting an indeterminate form, the derivative version is still eligible for a second application of L'Hopital's rule. So we'll apply it again. Since we're doing so, I'm going to again label with L'Hopital's rule just to announce our procedure here, our reasoning. So this is now the limit as x approaches infinity. So now I'm taking derivative of the previous version. So this is, again, derivative of e to the power of 2x is e to the power of 2x. And then using chain rule, derivative of the 2x is times 2. But now the derivative of the denominator is going to see the variable fall out. That's derivative of 2x, which is just going to be 2 times 1. And those 2's are going to cancel. So this really reduces down to the limit as x approaches infinity of e to the power of 2x. And that clearly is not an indeterminate form anymore. If I were to do direct substitution and put infinity in the numerator, or in the power, base to the power of infinity is infinity. And that completes the limit. So thank you for joining for an investigation of using L'Hopital's rule to evaluate limits. See you soon.